Hello, my name is Rohan.
Hello, my name's Anol.
Today we will be presenting the paper Understanding and Improving Fast Adversarial Training. Adversarial training is one of the defenses used to make a machine learning model robust to adversarial attacks. Improving the robustness of machine learning model is motivated not only from the security perspective, but such models have better interpretability properties and also generalize better. Recent works has been focusing on making adversarial training computationally efficient for deep learning models. Fast gradient sine method and projected gradient descent method are such algorithms that are fast enough to be computationally efficient for the deep learning models, but recent works have shown that such models are prone to catastrophic overfitting, which is a phenomenon that occurs when a model quickly loses its robustness over a single epoch of training. FGSM is a method to add noise whose direction is the same as the gradient of the cost function with respect to the data. This perturbation or noise is typically bounded by a small constant to limit the magnitude of the change in the input. PGD is an iterative method that involves computing the gradient of the loss with respect to the input and then modifying the input in the direction of the gradient subject to a constraint on the magnitude of the perturbation. L infinite adversarial training involves adding a constraint to the training process such that it limits the magnitude of the perturbations to the input in order to make the model more resilient to adversarial attacks. Catastrophic overfitting is a phenomenon in which the model quickly loses its robustness over a single epoch of training. The basic idea behind gradient alignment is to align the gradients of the loss function with respect to the inputs with the perturbation added to the input. As we can see on the figure on the left, a closer look at the evolution of the robustness reveals that using FGSM can lead to a model with some degree of robustness, but only until a certain point where the robustness suddenly drops. This phenomenon is called catastrophic overfitting. As a partial solution, the training can be stopped just before the point which leads to a non-trivial but suboptimal robustness. Previous works have an inherent trade off between the computationally efficient approaches which aim at solving the problem in as few iterations as possible and approaches which aim at solving the problem more accurately but with more iterations. Some researchers suggest the use of early stopping. It is a regularization technique used to prevent overfitting by interrupting the training process when the performance on the validation set starts to degrade. The idea is to save the model's weight when the performance is at its best on the validation set, avoiding the risk of overfitting to the training data. Some researchers also suggest the use of FGSM first and later on switch to the multi-step PGD, which is motivated by the analysis suggesting that inner maximization problem can be solved more accurately at the end of the training. These techniques either provide comparable robustness to FGSM methods or fail for an higher L infinite radii, or in the worst case, being as expensive as the previous techniques.
So I will be focusing on the main contributions of this paper, starting from section 3. The authors conduct an extensive analysis of existing fast adversarial training algorithms and identify several limitations and challenges, including a lack of robustness, limited generalization performance, and the requirement for extensive hyperparameter tuning. The question initially tackled was whether we really understand the failures of FGSM training. If you plot the accuracy of FGSM training models over epochs, you will observe that at some point it may lose its robustness, in the sense that its adversarial accuracy drops down to zero. At the same time, in PGD training, this does not happen. The main question of our paper is, can we overcome catastrophic overfitting and train robust models fast? To address these limitations, the authors propose a new fast adversarial training algorithm that leverages the geometry of the decision boundary to generate effective adversarial examples. This is achieved by first computing the gradient of the loss with respect to the input and then using this gradient to generate an adversarial perturbation that maximizes the loss. This approximation is much more efficient than computing the full adversarial loss, as it only requires computing the gradient of the loss with respect to the input. The decision boundary is the surface that separates the positive and negative regions of the input space. By considering the geometry of the decision boundary, the authors are able to generate adversarial examples that are more likely to fool the model and cause it to make incorrect predictions. To evaluate the performance of the proposed algorithm, the authors conduct extensive experiments on several benchmark datasets, including MNIST, CIFAR-10, and ImageNet. The results show that the proposed algorithm significantly outperforms existing fast adversarial training algorithms in terms of robustness and generalization of performance. The authors also show that the proposed algorithm is able to achieve similar levels of robustness as standard adversarial training, but with much less computational effort. The authors empirically observe that the following quantity, called gradient alignment, is directly related to catastrophic overfitting. This quantity is essentially cosine between gradient of loss function with respect to input at point x and x plus theta, where eta is a random perturbation. Idea of regularization method is to maximize gradient alignment during training, which essentially helps to scale adjacent training, also taking care of very high epsilons as compared to the previous ones. The paper also discusses the role of step size and randomness. The paper also shows that catastrophic overfitting occurs in single layer CNN, so it's not a property of complex networks only, and also analyzes gradient alignment at initialization. In conclusion, catastrophic overfitting is a fundamental problem not only for standard FGSM training, but for computationally efficient adversarial training in general. FGSM AT, enhanced by a random step, or AT for free, are also prone to catastrophic overfitting. Early stopping leads to suboptimal models. Grad align prevents catastrophic overfitting and improves the robustness compared to the other fast adversarial training methods, reducing the gap to multi-step PGD training. Finally, grad align leads to an increased runtime due to the use of double backpropagation. The authors provide a comprehensive analysis of fast adversarial training and introduce a new algorithm that significantly improves the robustness and generalization performance of deep neural networks against adversarial examples. Thank you and have a nice day.